ladies and gentlemen, good afternoon. I said good afternoon. So, sorry for starting so late this lecture. I came by train and okay, and it was delayed, so did I. I read more. Okay. Oh, it's slow. Great. So, one of you asked me about the requirements of this lecture, and I asked the same from the rest of the person of this course. I didn't get any answer, which is a pity and actually awkward. So, I modified the requirements of this course. So last time I told you, I will give you 5 homework. You have to do it 3 times, three of them for the signature, and then you can get plus points, 10% for extra homeworks. I will keep this. I also told you that there will be 2 midterm exam or test. I will modify this, there will be 1 at the end. And before Christmas, I suggest you before Christmas, we will write a written exam, and that written exam will be your grade. If I understand well, still, the Neptune, you will have 2 grades, 1 for the practice, 1 from the lecture, and that's it. Perhaps the responsible person, Professor Ratz, will modify this. I can offer this one. Why? I think you can learn everything based on what I record and present you, and if it's not necessary, I don't want to come so often here. That's one thing, and I think you will learn something useful when you attend the lectures and do the exercises. What else? The levels, the grades. For signature, you will need 14% for everything, for the test. Yes, and for, I don't remember, it was 50 or 55 or something like this for the passing score or something like this. That will be the same. But don't worry, you will be able to prepare for everything if you do the homework, if you listen, and so on. This is my upgraded requirements. Perhaps this will change if the guys will answer to my emails. It will be tough or tougher or something like this. I hope it will not. Okay, I will need your help. Please scream if you see something that you have seen. Part of this course was given to you. One is the Heisenberg undeterministic relation, and also last time I talked about the Dirac equation. But checking what you have done, you haven't heard about the classical theory of atomic structure, Rutherford, Frank-Hertz experiment, Bohr model, quantum numbers, Pauli exclusion principle. Have you ever heard about it? Have you ever had MRI examination? Do you know what is MRI? You know what is X-ray examination? You know what is CT? And you don't know what is MRI. Magnetic resonance investigation. There is a, do you know Dr. House, that series? Never? Yeah. You know, there's a big magnet you are put there, and then it works. If you have metallic feel of your reparation of your teeth, or any metal in your parts, it is taken because the magnitude of the magnet is 1 or 1.5 Tesla. It's huge. It's something 300,000 times more than the magnetic field on the surface of the Earth. You will understand how it will work at the end of the course. Also, you will understand how we can determine the material, what materials are in the stars. I mean this course, this lecture. Okay, and please tell me if something is familiar, because the subwatch have told. Okay, atom. Even the ancient Greeks thought about the structure of the material, and they considered the elemental part of all matter atom. That's something spheric stuff, and that's it. They had no physical or experimental experience for it. They just did it in a philosophical way. But we know what is an atom. This is the elemental part of, for example, metals or some gases like helium, argon, neon, krypton. Sorry for the pronunciation, that's the Hungarian pronunciation. These are atoms. The hydrogen, the oxygen, the chlor has molecules. It's something different. The question, which was very important 100 years ago, what is the structure of the atom? What is it? What is inside? They had some assumptions. There must be some positive and some negative parts. But what is the structure? How do they look like? The first model was this plum-pudding model by Thomson. Here you are. The atom has negative and positive parts. The sum is 0, so it's neutral from outside, and that's the structure. Okay. If so, then take some of particles, that's helium ion, proton, proton, neutron, neutron. They didn't know that. You know it from chemistry or someone else. And just shoot, lead through the material. This experiment was made by Rutherford. Well, very nice name. And there is a still Rutherford laboratory in close to London. And they took gold. Well, that's nice actually. But he didn't know that the gold atoms are quite large and the nucleus are large, but he didn't know that they are nucleus. So he took a source, a radioactive source, and there is a radioactive source. The radioactive source ejects nucleus of radiation everywhere. But it was put in a the metallic box, doesn't matter. I didn't sleep so much today again. And there was one hole on it. Actually, for alpha and beta radioactivity, a paper, your skin can protect you from that radioactivity. However, if, for example, what is it? Radon or uranium or plutonium goes to your bone here, where the blood is made, then you are dead. It's a poison, and it also destroys the DNA, your DNA. But they didn't know it. We know it. They had some ascension because Marie Curie died and in cancer and everything, but doesn't matter. So there was one beam, there was a hole, it's like, it's a box, one hole, there's a beam. Beam of, now we know, alpha particles, helium ions. And they let it through gold. The gold is a very good material, not because it is nice, its conductivity is high, and if you have such piece, you can cover very large area. I mean, from one gram is enough to cover this place. You can make very thin foils. Really. That's why they use the gold. The expectation was that the particles will go through. And that's it. What we get, experiment, is the other particles had large scattered at large angles, so they deviated, and that was bad. This cannot be explained by this plum cake model, the Thomson model. So it seems to be there is a structure of the positive and negative ions. This is the explanation. It seems to be there is a nucleus of all atoms, which is positive, like the alpha particles, and somewhere, somehow, outside are the negative electrons. And this is the Rutherford atomic model. You can see beams come, I mean a particle come, and go through. But some of them scatter. This is the experiment, and this is the explanation. However, based on your, well, actually not, because you haven't learned electrodynamics. If a charge accelerating, then it radiates electromagnetic waves. I know it from the pulsars, because I am an astronomer. The pulsars are dead stars, consist most of neutrons, and they have large magnetic fields. And this magnetic field traps ions, protons, electrons, and they are rotating around the magnetic field in this way, and emits radiowaves. So, we have this Rutherford model. There is in the middle the positive nucleus. They didn't know what is neutron, proton, anything, just something positive. It has a nucleus. The electrons are rotating around it, and that's it. The problem is the following. If a particle, a charge particle is rotating, accelerating, rotation is acceleration actually, because the direction changes, the direction of the speed, then we expect radiation. Even when there is no excitement or anything, just we see a hydrogen atom and it should be radiated. We don't experience it, so that's a problem. So this model is better than the Plum model, the Thomson model, but not perfect. This is how they do the spectral analysis. Do you know what is spectral? Do you know what is prism? Prism? You know? There is light, white light, and you lead through a prism, and you got the rainbow colors. That's okay. However, if you look carefully, more carefully with lights, you can see in the spectra lines, spectral lines. Some lines are lighter, brighter than the neighborhood. They are below its emitting lights. Some of them are darker. They are not emitting, they are absorbing, thank you, sorry. I'm a bit it's not visible, but my mind is not good when I don't sleep so much. Okay, we have this. We see this, then we have to explain. This explanation leads far, very far, to this Facebook and internet and space travel and everything. Someone, I don't know who, it's not important to know, said, oh, the stars are so beautiful and also the sun, but we will never know what their material is. Never say never. These spectral lines are related to the material of which is between perfectly back emitting thermal radiation and us. So some radiation comes from the sun. There is everything on that spectrum, and there is something in the sun's atmosphere. It's funny because it's a plasma ball, so there is no surface. For example, there is hydrogen. The hydrogen has its special spectral lines. Also, the nitrogen, oxygen, nitrogen, whatever you do. One of these important spectral lines are the Warner lines. This I will show you how it looks like. This provides you some lines in the spectrum. I show you. I think that's the best. This is the spectrum. Everything is start from. Okay, one is upside down, doesn't matter. But start from blue to red or red to blue, doesn't matter. And there are special lines. The first, on the top, are the spectral lines of hydrogen. The next one is the helium. And then you can see neon. You know from chemistry, the hydrogen has 1 electron. The helium has 2 electrons. Neon has 10 electrons. And the difficulties of the lines are, and the number increases. Some reason. We don't know, we don't know why, but it has a reason. The simplest thing, the experimental red is the hydrogen. Actually, the hydrogen is not so simple. You can see the hydrogen, it's light and it's nothing. But in high temperature, the hydrogen could behave like chlor or fluor, and at high pressure, for example, in the core of Jupiter or Saturn, it could be metallic. It's a very, 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 very weird actually, but it looks strange, simple. So strange that you can calculate the hydrogen atoms' energy levels and everything if you solve the Schrödinger equation that you already know. We are going approaching to the Schrödinger equation right now. Just you don't know, don't you? So one of the spectral lines are the Warner lines. It's a quite old experiment. It is actually in infrared, and it's very important in astronomy. There are small stars. Their mass is 1/10 of our sun. They called red dwarf. Their radiation comes in infrared and red. There is something which will become the non-red giants. Their surface also has low temperature, and it also comes from so the spectral maximum there also in red and infrared, but it's a different stuff because it's polluted with metals. In astronomy, in astrophysics, everything is metal, which is not hydrogen or helium. So red dwarfs are better examples. So the red dwarf spectra is full of hydrogen spectra is full of this Bohr. There is this Rydberg guy. He extended this experimental formula. Okay, you should have told me something. The lambda is the wavelength still, n is the number of the line. It starts 2. It could have starts 1 actually. It's an other series. I will check what is its name. And this is a generalization, this Rydberg formula of the place. The place means wavelength of the spectral line. Here, so this is actually different wavelengths or frequency, whatever you prefer. You prefer frequency actually, but doesn't matter. Okay, Hertz. You know very well this name, Hertz, from frequency. He made an experiment, and sorry for the Hungarian text, with mercury stream. So he had this experiment, cathode, anode, it's positive, it's negative, the voltage was high, and it was full of mercury stream. It was not a perfect vacuum. So these guys gave higher and higher voltage, and then the current that was indicated or led through this tube had peaks. It means this mercury has some very interesting behavior. There are energy packages that they can receive. Certain packages. We will check the electron structure of the mercury once we know what is the electron structure. This is actually what they see, but in different way. The wavelength, the quantums, the steps, the energy depths what the material, the gas can absorb. So there is this Bohr atomic model. This is like the Newton gravitation theory, because Newton gave the formula of gravitation that he did not explain. So he knew that and could calculate the orbit of comets or planets or the moon, but he didn't know what is the real reason of gravitation. 300 years later, Albert Einstein in general relativity theory explained that gravitation is a distortion in the space-time. But Newton didn't know it. That's the same. We have nucleus, and around it, on circular orbits, of course, everything is cubic, everything is circular, everything is spheric, because we can calculate with this. You know, if you know fractals, you know that the nature is not in this way. So we have a nucleus that's positive, and the negative electrons are around it, rotating around it on certain orbits. All orbits has an energy and also a magnetic moment, and the atom could absorb only those energies which are between these pockets. So there is one energy amount which belongs to n equal 1. There is something which belongs to n equal 2, and there could be something, so the atom can absorb the difference of these energy pockets. You will see what it means. That's why the name of this field is quantum mechanics, because we have quantums, we have steps. we have a limited amount of energy that could change. Yeah, that's not the experience of what you can see in the nature. Yes, and there is no radiation. It should be radiated because they are accelerating, they are on an orbit, but they do not. He could not explain why, but he did. You know that Bohr was a Danish scientist. Have you seen Oppenheimer, the movie? I suggest you to see it. The director is the same like Interstellar, and it's a very hard, very tough movie about the personality of Oppenheimer. He was not the same. He made the first nuclear bomb, and also Bohr and some Hungarian scientist shows up. For example, Edward Teller, but he was not like I met him. He was not like in the movie, not big or something like this. Doesn't matter. Okay, we have these levels, energy levels, and there is energy exchange and jump between only these levels. That's the most important thing. We can calculate this, and this jump could be calculated with the Planck constant multiplied the frequency of the radiation. This is how it works. Okay, so this is how it works. We have an atom. It has a radiation. It hits the electron. The electron goes on another orbit, and then it's bored there, or using the energy minimization principle, it jumps back, and the difference of the energy of this orbit and this orbit is radiated. This explains how the spectral lines are made, but also explains something else here, these lines. Here, I don't know what is inside, but in the old days, we call this neon tubes in Hungarian. There was neon, it's very expensive gas actually, and there was some high voltage on it, and it radiated certain frequencies. Something similar happens in LED lights. They are more brighter. There is a lightning diode in it. You will learn from me what is it, how it works. And it emits a certain light. In the old days it was green and red, and now we have white. If I remember well, the guy, was a Japanese guy, made this, invented this, and got a Nobel Prize with others. Funny thing is that by that time he left the science and worked in industry, because it's quite tough to get a permanent job in the science. There's another, so Nobel Prize is sometimes not enough. I'm kidding, but not 100% kidding. If you see something and you cannot explain why you see it, that's, well, it's irritating, that is for scientists. For some of them, younger, also young kids. Later, people forget how to use their brain and then they doesn't matter. So Bohr introduced this angular momentum, and this is the formula. The mass of the electron, the radius of the orbit, speed, and then that is Planck number divided by 2 times p and multiplied n. This h, I don't know what, That's the Planck number, modified Planck number that we usually use. I don't know why, but it's close to 1 and it's easier to calculate with it. So we have this number and H line, or I don't know, and the angular momentum of electrons could be an integral multiplication of H. And this is the principal, the main quantum number, M. We will return for this because it has a different meaning, but this was the first approach. The Born model was a little bit modified because they looked in high resolution, they looked at the spectral lines, and it has some fine structure. This fine structure was explained, okay, the orbits are not circular, they are elliptics. So they have azimuthal orbital quantum number. Not this is the reason actually, but they introduced it. And now we are arriving to the MRI examination. Zeeman was, what is the name, Dutch scientist, and he recognized that at strong magnetic field, the spectral lines are split into 3. He didn't know why, but that was the expression. This is the way how we measure the strength of the magnetic field on the sun or in a star. We know the material from the spectral lines, and also we know the magnetic field because of this. When you have MRI examination, your body, okay, why is important this MRI examination? Well, half of you will have problem with the backbone. I actually do. I had classmates in secondary school who were heavy athletes with a lot of muscles. Also, I had classmates with very skinny. They, all of us had a problem with our backbones. And then the X-ray will not help you because the X-rays helps you to see the bones. CT could help you, but if you use huge magnetic field, then and you split in the water of your body, there is hydrogen, and you split the spectral lines of this hydrogen, then you have an image about your soft parts, your soft tissues, not the bones, but the discus between the hernia discus, or the joints as bones, and also there are soft tissue around it. So the MRI examination is for this, and this split of the of the spectral line by strong magnetic field, this is help. The split is small, so you have radio waves only, a few centimeters with a few centimeters wavelength, but it's important. So you will have a grayscale image of the hydrogen density in your body, and with a lot of software and everything, you can see how your backbone look like. Not only the bones, but the disc and everything. And also, it is easy to see how your brain looks like, or a fetus in the belly of something. The high of a woman, the high means Tesla. 1 Tesla, 1.5, 2 Tesla. It needs a lot of energy. So if usually in the hospital they have a independent power supply, because if there is any problem, then breaks everything around it, but it's useful. So this game to check the lines in spectra, which is nice, lead something important medical examination. Okay. To explain this, they introduced the magnetic quantum number. There was a main or principal quantum number. There is, what is the name? Orbital or secondary quantum number. And now we have the magnetic quantum number. And this magnetic quantum number, you have the electron, charge of the electron, the mass of the electron, and also the Planck constant. And so there are three, for example, for one electron, north, south, and the middle. This is why there are three lines that they introduced. They also didn't know why it happens. And now the most important stuff is coming, the spin. This spin is an angular momentum. Its magnitude is with this number, Planck number, and so on. And it's the fourth quantum number. Main, secondary, magnetic, and spin quantum number we have right now. We don't know why, but we have it. That was experiment. And there was another interesting experiment or observation, this Pauli exclusion principle. There could be only one electron in one orbit with the same main, secondary, magnetic, and spin quantum number. I will explain you this. The hydrogen has one electron. The helium is a very stable atom, gas, material. It has two electrons. But all orbit could be maximum two electrons with different spin quantum number. It has something very important consequences, but the approach is not from the consequences. In the 19th century, Big Bird, Russian scientist, chemist, recognized that the elements has very similar behavior. The hydrogen, the lithium, the natrium, the fluor, the chlor, the brome, they behave very similar. Also the helium, the neon. What? We recognize that the atomic mass, the mass, but the atomic mass, if you consider the atomic mass, then you find periodic behavior. And based on it, he saw leaks, elements that they haven't discovered. And he predicted that will exist. That was the chemistry, and they didn't know what is the reason. And also irritating, but now we will know. And now I need your help. You have heard about the Schrödinger equation. That was the only thing, and Heisenberg answer to the principle that you heard before me. There was a quantum mechanical equation, the Schrödinger equation. You learned it. I saw in your books. That equation is a complex equation. You can solve it. I shut the door, give you papers, you use a polynomial, actually spherical functions, and after a few days, the survivor who had the hydrogen atom solved. Actually, the Schrödinger equation in the Coulomb potential, that's the hydrogen atom, has the resolution, the energy levels of the hydrogen atom, and also the form of the wave function, the probability wave function around it. If you fix the Schrödinger equation, you got the Borner lines, you got these energy levels, and also you will got the main quantum number, the principal quantum number, the orbital quantum number, the magnetic quantum number, and the spin quantum number. That comes from the Schrödinger equation. I suppose that you heard about it. This is a task. I have to pass an exam from it. If someone gives you a task to calculate, for example, the electron structure of helium, that stuff perhaps you can send into the hell because it is not possible to do on paper using computers. I had a test, midterm test, when I had to do the calculation of the electron structure of beryllium atoms with 4 electrons. And it was half of the points, and it was not enough for the classes. Actually, 2 guys could do it in my very good class. It doesn't matter, somehow we passed, but it was not really a fair stuff. However, this is beautiful. The original stuff is this. I will return for this and apologize for the Hungarian text. This is what you can see is the you haven't known it, but this is the periodic system that you have seen. And I talked about the periodic system of the elements made by Mendeleev and others. What you can see, you solve the Schrödinger equation for hydrogen atom, and you have first main quantum number. The main quantum number is the distance of from the nucleus, from the core. That's the main quantum number. These shells. One is the first, the second is the second, the third is the third. But this is bad. This is not how the atom look like. So the hydrogen has one solution for the main quantum number n equal 1. That's spherical. According to the Pauli principle, only 2 electrons could be that orbit. This is the hydrogen and then the helium. There is also a law. The maximum number of electrons is of atom is something twice n squared. So if n equal 1, there could be only 2 electrons. So on the closest orbit, the low energy orbit of the hydrogen would have only 2 electrons. You can excite it, and then you can have larger atoms, and you can reach higher main quantum number. But on normally there is only one orbit, one s. If you pass and you go to the lithium, then you have something inside which is full, and there is something, a shell, where there is one electron. But here the main quantum number is 2, and it leads you something else. So if you have an excited hydrogen, or you have a lithium and then beryllium and boron and other atoms, when you have more and more proton in the core and more electron around it, you have a shell with main quantum number 1 with 2 electrons. Then you could have 2 other electrons on the n equal to main quantum number. The shape is like this spheric. But at that distance, the maximum number of the electrons could be 8. And then the Schrödinger equation has it has another solution, this infinity, 8, what is its shape? So the next shape. The first name is S, the second name is P, and this P is something 8 in this direction, Z, X, and Y. There are two electrons in all of it, so altogether it could be 8. Go back to the periodic system. We filled the first shell, hydrogen, helium. The helium is extremely stable. It's a noble gas, in Hungarian at least. Also the neon and the other, because its electron structure is closed and very stable. Okay, let's go forward to lithium. The lithium is, well, you know lithium, your cell phone is the battery works in lithium. Many of them. If you put in water, that's bad. Also with natrium and also with gallium, it takes the hydrogen from the water and ejects the hydrogen, and then it flames. The beryllium is a very good material. It's a very good array of metals for plants. The boron, well, the boron, its nucleus is very good. It emits, absorbs neutrons, and also, yeah, it's good. Carbon is very familiar. We are made of carbon. And then the nitrogen is a very stable. The oxygen is a very aggressive gas. You know it's a poison. Well, there are two approaches and answers for it. The oxygen is deadly, so we are dying, and because breathing it, and after a while we will die. But in serious, if you have clean oxygen, because you dive, and its atmospheric pressure is 26 or something like this, then it's a poison. And also, if you broke the molecule of the O2, the oxygen, then its behavior is like the chlorine. The chlorine is a very aggressive gas. The next one is fluor. You know fluor. The fluor is very good. If you have a fluor acid put in a glass, then it dissolves the glass. It also dissolves the gold, silver, and platinum and everything. There is something that I cannot explain you, but I think someone else also cannot. Here, there are two laws. So you can see this S, the first spherical number, and then you can see the P, and then the D will not show up. We have natrium, magnesium, aluminum, silicium, phosphor, sulfate, and chlorine, and also argon. Their behavior is very similar. Lithium and natrium makes hydrogen with water. Also, they are very good to make different salts. The magnesium is very good. It's light. It has a very bright light if you burn it. The bore and the aluminum also has very similar features. 3 electrons. The carbon and the silicium also have very similar behavior. The diamonds and the sand, the silicium or the clean silicium, has a very similar structure. There is something else. Do you know the Dune? The movie or the novel? Did you see Dune? Dune. Okay. There are these walls. For the movie you will not know, but they are what is the name? So they are a different type of in this universe. There are different type of living metabolism. They have a different type of metabolism. They are based on silicium. There is a theory that we are here and we are carbon-based, and it's possible to have silicium-based metabolism. Also, this sulfur is very similar to the oxygen. Arthur C. Clarke, who invented the communication satellites a long time ago, and also he was the expert of moon landing and electrical engineer like you, and a very famous sci-fi novelist, writer. Suppose that, and other scientists, that there could be some life around the Jupiter, on the icy moon of Jupiter, Europa, Ganymedes, Callisto. Also now we have a new candidate at Saturn called Enceladus. There is water, liquid water, because the tide force of the giant planet makes the core and some shell liquid. And they suppose that there is some life, but it's not based on oxygen, but sulfur. That's hypothesis, that's fantasy, but it's also possible. The flow and the core is similar, that's nice. Okay, let's jump back. On the main quantum number 3 should be d orbits. This is the shape, this is the shape. You know, you have the Schrödinger equation, you have energy. The energy is came from the complex eigenvalues of the operator, and the eigenfunctions, probability functions, and this gives the probability of the location of the electron. The first is spheric, then we have this infinity over 8 shape, and then, I don't know, we have this P. It's more difficult. I hope you can see how it looks like. And we can go back to here, and we have this third, and so we have this field. Here, the electrons fill up after the S and P, the d orbit. And at the very end, here, we have other solution, the F. It's much more difficult, and these are here. Londonides and actinoids. And here you can see many elements like uranium and where is the yes, uranium, and the second is plutonium. You know, if you like nuclear explosions, then you like these elements. Oh, sorry, nuclear power plants or something like this. Also, there is something California. These are large electron structures, and also the core is large and unstable. Most of them are radioactive. To explain the radioactivity, you need quantum mechanics, and it's much more difficult than the electron structure. Here, it's supposed to do, to explain the same that I tried to explain you. Sorry for the Hungarian text in the, okay, important. Did you see that I uploaded all materials to the Moodle? Okay, great, you will learn information. So, for the final version, there will be only English text. Sorry, just I had no time to change it. What you can see, name or principal quantum number, that's the first. Then the secondary or orbital quantum number, magnetic quantum number, and then this spin quantum number. Also, there is some conversion how you designate it, you show how you call these layers. And you can see also the maximum number of the electrons. This is what I try to show you with this and explain it. It's not simple. If you do not understand, the problem is not with you. Also, you can see something. If you have lithium and you want to calculate lithium, then you have 3 electrons, for example. Then usually you just say, okay, we have a closed shell at first. We don't deal with it, and we deal only the 1 electron on the second shell. Well, the result is not good, but it's better than nothing. Okay, I will show you something, but I return to the end of the last lecture, the previous lecture. It's Dirac equation. In the Dirac equation, the Schrödinger equation are unified in special relativity theory. And now you can understand why is it important that it gives the mass and the charge of the electron and also the positron, and also explains the spin, because the Schrödinger equation and also this Bohr model and modified Bohr model, Bohr-Zonneville model, do not explain why the spin and these quantum numbers exist. So this is why is it important, also because of the antimatter and other things. Now return to let's return to here. You told me that, and I saw that there was some experiment about wave-particle dual feature of particles, but you never heard about the Broglie equation. I saw it in your notes. So you never heard about, because we start to do some exercise, and you never heard about the Broglie, but you have seen this equation. I have seen in the notes these equations, not equation, experiments. Okay, this is a very hard stuff. It is very difficult to understand what is going in quantum mechanics. It is We talk about it because you need to know how a photocell, how a light, and how a conductivity or how semiconductivity, a diode or a transistor works. You need quantum mechanics, the basis of quantum mechanics, and as electrical engineers. Okay, which is very difficult that we are both particles and waves. You have seen this at photon. The photon has geometrical optics. For a long time we don't do it. And also it has wave features like decreased like interference or something like this. The following experiment will prove that the electrons, the protons, the neutrons, the hydrogen atoms, the hydrogen molecules, even you have wavelength. And all of us are wave and particle together. But at this size, even your size, it's much smaller than mine, so it's not notable. But on the range of the elemental particles, you can see. Okay, back to the material. Louis, okay, there is something bad. It's impossible. It's impossible. Can someone check the lifetime of this broccoli? Please. I'm going to use my cell phone. Not this one, when he died.
Yes, correct.
That's very interesting. He lived long because he knew Marie Curie, and I thought he lived earlier. Doesn't matter. So, the light and matter actually both particle and wave properties, I told you. De Broglie introduced this formula, which gives the wavelength of a particle with a certain speed and mass. And the mysterious Planck constant appears here again. Do you know Marie Curie? Marie Curie? You know Marie Curie? You know Marie Curie? She was originally in Poland, get married to France with what's the name? Someone, a French scientist, and together they did a lot of things. And she was the first woman who got Nobel Prize, and she is the only person who got 2 Nobel Prizes. First for physics and one for chemistry. He died in cancer because he discovered the uranium, polonium, not uranium, they know the uranium, he discovered the polonium, he discovered the radon, radium, the radon, it's a product of radium, and what cancer later. Her daughter, Irene Joy-Curie, also got Nobel Prize, actually. So he was very, very famous and lived in the same time like De Broglie because she applied for the membership of the French Academy of Sciences, and then they had a competition. But both of them were real scientists. Imagine that in that time, many people could not write and didn't know anything about science or light or anything, but they used their brain and they meditated about these problems. So here we have the final formula, the length of a particle with certain impulse, the speed is impulse, m times mass times velocity, is this. Here we also see this Planck constant. We saw it in energy test spectra, we saw in Compton scattering, we saw at photoelectric events. They had an experiment. The experiment was that using the crystal structure of a metal, they made electron diffraction. What it does mean? What does it mean? Sorry. Okay, first, you have light, and you have one slot, and then you got one link. That's okay. You have particles. Okay. You have two slits, you have light, and you got interference in that way. You know what is interference? Interference of waves. You know what? You don't know? Interference. Okay. This is from. So if you have and you have waves. For example, this is just water, and you put something straight, ruler or something like this. Then you will get this type of waves. If you do the same, but you have two slots, you have waves. Then you got something like this. So the waves will fill a pattern during the summer. You split some oil, and the oil is, for example, the surface of a slim material or on the water. You can see the colors of the rainbow. Do you remember what I mean? This is also an interference. This is the ground. This is some water. And you have oil. The oil is necessary because it can spread. So a drop of oil could be very, very large. So this layer could be a few hundred nanometers. So the light comes, turns, and also another comes and turns, and so they will form different wait. It's not that one, it's not interference, it's like a prism. Oh, where you can see interference. Okay, forget this. So in water, in the sea, you can see this. Now I cannot tell you any. This is just diffraction, not with refraction and not interference. Is it understandable? Okay. Very important thing. You, with advanced experience, you can emit only one photon or a very low number of photons. You have one photon, you have one slit, and it has one line on the other side. If you have two slots, then you can see this. Well, this is what I wanted to write. You can have these interference patterns with one photon. Actually, it's normal if you have more photons or stronger beam, but this is one photon. And you have interference pattern, but you already know that the photons are particles and waves. Let's do the same with electrons. You have one electron, you have one slot, you go through, okay, that's a particle. You have two slots, and you could have interference pattern, and perhaps I change somehow or mix the plots, but you have this pattern too with one electron. So the electron is a wave. It has an application. You know microscopes. Have you ever heard about electron microscopes? You heard about it. You have electron, you use instead of photons, electrons, and you would have much higher resolution because the light resolution, the visible light resolution, could be a few hundred nanometers. But the electrons could go through. You know microchips. Microchips, originally they just checked and mainly wanted to check with microscopes. Some of them, it's not so bad. But it's better if you use electron microscope. And the electron microscope also can see the viruses. With normal microscope, you can see cells. You can see bacteria. But the viruses are much smaller. They are inside in cells. So they use electron microscope to it. There are also some terrible images of insects, spiders, or fly, or anything with the hair and anything. This is what they use for that resolution. Also, you can do the same with neutrons. The neutrons has the advantage is that well, it has a higher resolution. Also, there is something that is not written here. This electron diffraction, you can do interference with light. In a crystal, you can do the same with electrons. If you have neutrons, for example, in my institute, in the Wigner Research Institute for Physics, we have a nuclear power plant. They have neutron diffraction. You have a coin from a Roman coin, and there is mark on it, and also some dirt and some pollution. You can go through with neutron diffraction and see the original material. Also, you can take a big propeller of a turbine from a water power plant, and you can see the microscopic cracks in it. It's very difficult because it's, I don't know, 10 tons or something like this, but they need this material stuff. That's for neutron diffraction, and that's the application of electron diffraction. Okay, let's go flow, and this is well known because it was introduced these Hermian matrices and everything. You cannot determine the position and the impulse of a particle. There is an uncertainty relation. That's the Heisenberg uncertainty principle. You have heard it. You have heard about it in the first 4 classes. At least I saw in your notes. Also, you cannot determine the energy of the particle. There is an uncertainty, always. And this uncertainty, the minimum of this uncertainty, is also the Planck number. There is something which they call the deduction, doesn't matter. And here is it. So you cannot determine the, okay, I will improve this. You cannot determine the position and the impulse of a particle. That's the Heisenberg principle. Which is, we should understand, it is not possible to determine the location and the impulse of a particle. It's like the mass and energy are the two sides of the same thing, two features of the material which are compatible. This is something that we must accept. The nature is quantitative. There are energy levels that an atom or anything can take. The nature is uncertain because we cannot measure with infinity or very high accuracy because there is some restriction for it. And this is what I have told you, this Dirac stuff, and this is the end of the lecture. Thank you very much. So let's take a coffee break, and then I will continue with the practice. Okay? Thank you very much for your attention, and stop this one. And also